Welcome for the next class. Now in this class we will discuss about arithmetic and logical instructions. So in previous class we have discussed about the data transfer instructions. Now we will discuss arithmetic and logical instructions. So all arithmetic and logical operations. So in this group we will use the instructions to perform the arithmetic and logical operations. The first instruction is add ax comma bx. So in this particular instruction add ax comma bx, so here the first operand is indicating the source and destination, the second one is indicating the source. So here what it does is add ax comma bx. Now content of bx will be added with the content of ax and the result is stored in ax. So that is ax is equal to ax plus bx. So here the content of ax and content of bx will be added and the result is stored in ax again. So that is the first operand is indicated as source and the destination. Okay. So after addition, whatever result we are going to get, based on the result, the status flags are being updated, like a carry flag, parity flag, auxiliary carry flag, so sign flag, zero flag, all these flags will be updated according to the result of operation. That is add ax comma bx. The second is add with carry bx comma cx. In this case, the content of cx will be added with the content of bx along with the carry flag. So before this instruction is being executed, whatever carry flag is there, that carry flag is being used. So with this operation of ADC bx comma cx, so content of bx will be added with the content of cx along with the carry flag, and whatever result is being obtained is stored in the bx. So bx is equal to bx plus cx plus carry flag, that is so add with carry. The third instruction is increment dx, for example. So increment, so the specified content will be incremented by 1. So in this particular case, increment dx, the content of dx will be incremented by 1, that is dx plus 1. So the result will be stored again in the dx register. This is about the addition part. Next comes to the subtraction part. So next instruction, subtract bx comma ax. In this example, so the content of ax will be subtracted from the content of bx and the result is stored in bx. That is bx is equal to bx minus ax. So content of ax will be subtracted from bx and the result is stored in bx. So based on the result, the flags will be updated like carry flag, auxiliary carry, that is now carry flag is nothing but borrow flag, sign flag, zero flag, all these flags will be updated accordingly. So next instruction is subtract with borrow, SBB, subtract with borrow ax comma cx. So in this case now again carry flag is being used. Okay. So the content of ax, result is stored in ax. So ax is equal to ax minus cx minus carry flag. So that is subtract with borrow. So content of cx and carry flag will be subtracted from the ax register and the result is stored in ax. Next is decrement the content of cx. So here the cx content will be decremented by 1. Okay. So even if it is for example, if I want to use say a decrement CL, same. So here CL is equal to CL minus 1. So as per our requirement, we can use either 8-bit registers or 16-bit registers or any memory location also. So that is about the decrement. So subtract with borrow, decrement. and another instruction is compare bx comma cx. So, if you want to compare two quantities, we will be using this compare instruction for comparison of two quantities. That is, so in this particular case, so the content of bx minus the content of cx, it is going to perform the subtraction operation only, but the subtraction result will not be stored anywhere. So, content of cx will be subtracted from the content of bx, and based on the result the flags will be updated. So, if bx is equal to cx, then 0 flag will be set equal. Okay. If bx is greater than cx, then sign flag is reset. If bx is less than cx, then sign flag is set. If bx is greater than cx, then sign flag will be reset. So, based on the result, the flags are being updated, but the subtraction result is being ignored. So, this is specifically used for comparison purpose. Generally, the comparison operation is used for using as a condition to perform some other operation. So, if the content is less than the second one, then do this. If the first content is greater than the second one, do this like this. If you want to use any conditions, so in that case generally the comparison instruction is being used. The next instruction for the arithmetic logical group is negate. So, the negate ax, here the content of ax is converted into 2's complement form. So, negate operation is for conversion into 2's complement form. Suppose ax is having say plus 15, then after the negate ax, so ax will have minus 15. So, the negate operation is going to convert its 2's complement form. So, the positive quantity will be converted into negative, or negative will be converted into positive. Suppose if ax is minus 20, after negate operation it is going to be plus 20, vice versa. So, that is the use of negate operation to convert into 2's complement form. The next is multiply bx. So, this is multiplication operation. So, in this multiplication, so here only one operand is specified, that is multiplier. So, here we are going to specify multiplier with the multiplication instruction. Multiplicand is by default in accumulator. Remember, for multiplication and division operations, so for multiplier operation, multiplicand is in accumulator, multiplier can be anywhere, and in case of division, dividend is in accumulator, divisor can be anywhere likewise. So, now when we are saying multiply bx, so what it does is, so dx and ax is equal to ax into bx. So, here ax is having the multiplicand, bx is having multiplier. So, that multiplier is specified in the instruction, and when now that means now we are multiplying a two 16-bit numbers, then we are going to get the result 32-bit. So, 32-bit result to store, no register is available. So, lower by 16-bit result is stored in ax, and upper 16-bit result is stored in dx. This is the default assignment in case of multiplication. So, 32-bit result, when you are multiplying two 16-bit numbers, so we are going to get 32-bit result. Then out of 32-bit result, lower 16 bits in ax, upper 16 bits in dx. So, the multiplication can be between 8-bit with 8-bit. Likewise, suppose I want to multiply, if I say mulcl means, so this will give us ax is equal to al into cl. So, two 8-bit numbers. If I am specifying multiply with 8-bit means two 8-bit numbers will be multiplied and result 16-bit in ax. So, that is how multiplication. Now, this MUL instruction is for unsigned numbers. So, for all unsigned numbers you want to do the multiplication, MUL is the instruction used. Similarly, IMUL, so integer multiply. So, this is for signed multiplication. If you want to multiply signed numbers, suppose I want to multiply 5 say into say plus 20, then signed multiplication. Now, we have to use IMUL. You have to use IMUL. So, again this 8-bit multiplication with 8-bit, multiplicand and multiplier should be both 8-bit or both should be 16 bits. So, that is this multiplication instruction. Okay. And suppose I want to multiply a 16-bit number with 8-bit number. If I want to multiply a 16-bit number with 8-bit number. So, multiplicand is 16-bit, multiplier is 8-bit. So, for that now I cannot multiply this directly, but I want to multiply 16-bit number with 8-bit number. So, for this what I have to do is I have to convert this 8-bit multiplier into 16-bit without changing its value. So, for that we will be using the instruction called convert byte into word. So, this is going to convert byte into word. So, what this does, 8-bit number is converted into 16-bit number. That means, it is going to do the sign extension. Suppose I have an 8-bit number is say 00111010. Okay, if this is the number I have, now this will be converted by using the convert byte into word with. So, here the sign is 0. So, upper 8 digits will be zeros and lower 8 bit will be as it is 00110101. This is how my 8 bit is being converted into 16 bit. Suppose I have 8 bit is 10110001. For example, this is my 8 bit number. Then this will be converted into 16 bit as sign extension. One is sign. So, first upper 8 bits are all ones. So, lower 1011 0001. This is how the byte is converted into word, or 8 bit is converted to 16 bit by using convert byte into word. Now, this 8 bit I am going to convert by using CBW as 16 bit. Now, I can do 16 bit into 16 bit multiplication. Okay. So, for that purpose, this conversion of byte into word instruction and conversion word into double word is being used. Okay. Here conversion word into double word. So, 16 bit is being converted into 32 bit using the same concept, sign extension. So, the sign bit is being extended. Okay. So, that is this. The next is the division instruction. So, division BX. So, remember, multiplication is 8 bit with 8 bit, 16 bit with 16 bit, but the division, now the BX is indicating the divisor, division divisor. So, now the division will be always 32 bit is divided with 16 bit or 16 bit divided with 8 bit. So, I cannot divide 32 bit, 16 bit, 16 bit. So, I can divide 32 bit with 16 bit and 16 bit with 8 bit. So, if I want to divide 32 bit with 32 bit, so the 16 bit divisor I have to convert into 32 bit by using the convert word into double word, and if I want to divide two 16 bit numbers, then 8 bit divisor I have to convert into 16 bit by using convert byte into word instruction. By using this only I can convert and then I can divide. But the thing is, so I have to see here, here I have to, if I want to divide 16 bit with 16 bit, so 16 bit dividend I have to convert into 32 bit, then I can divide. And I want to divide 8 bit with 8 bit, so 8 bit dividend I should convert into 16 bit, then I can divide. So, that is, so the division operation, so 32 bit with 16 and 16 with 8 bits. Now, when I am using this say 16 bit, so where is my 32 bit dividend? So, in this case my 32 bit dividend is in dx and ax is divided with bx in this example. Okay. So, upper 16 bits in dx and lower 16 bits in ax. The 32 bit data is being divided with 16 bit, and the result, whatever result we are going to get. So, the result remainder in dx and quotient in ax, that is what it is going to be. Suppose I want to divide 16 bit with 8 bit, then I can say division with say ch, for example, that will divide ax is divided with ch, and al will have quotient and ah will have a remainder. So, that is how the division part. So, this division instruction is for unsigned numbers, and integer division, I division is for signed numbers. So, that is about the arithmetic operations, addition, subtraction, multiplication and division. Next, we will discuss about the logical instructions. So, logical AND, OR, XOR and NOT. 4 logical operations can be performed directly in the processor. So, first AND AX comma BX. So, in this case the content of BX will be ANDed with the content of AX, bitwise ANDing operation. So, here the bitwise ANDing operation between the contents of AX and BX is performed, and the result is stored in AX. So, that is AX is equal to AX AND operation with BX. Similarly, OR operation, XOR likewise. So, OR BX and DX. So, BX is equal to BX OR with DX. Similarly, exclusive OR operation, BX is equal to BX exclusive OR with AX. Likewise, we can perform the logical operations with this, and not AX is going to perform the complement. So, AX is equal to complement of AX. For example, before the operation AX is say 0 0 0 like 16 0 0 0 1 1 1 1, like suppose this is the example of, let us assume that this is 16 bit. Then after the complement operation or not operation, the result is going to be 1 1 1 1 1 and 0 0 0 0 0 0 likewise. So, this is how the logical operations are being performed. Okay, this is about arithmetic and logical instructions. I will stop at this point. So, in the next class we will discuss about some other instructions, some other group of instructions. So, thank you all.